So what we're going to do here is we're going to go over a couple textbook questions on electrochemistry. So basically this section is going to look at balancing redox equations in both acidic and basic or alkaline conditions. We've done a little bit of work in class, but we're going to work a little bit more on this idea. So, to start, 2016 says indicate whether the following balanced equations involve oxidation and reduction. If they do, identify the elements that undergo changes in an oxidation number. So for A, we're just going to work our way through. We have +3 for phosphorus, -1 for bromine, but there's 3 of them, so it cancels to 0. Oxygen's always -2, unless it's in peroxide. So there's our oxidations, so our oxidation numbers, sorry. So phosphorus goes from +3 to +3. So it's not, phosphorus does nothing. Bromine's -1 and -1. It does nothing. Hydrogen's +1 to +1. It does nothing. Oxygen is -2 to -2. Nothing happens. Or at least no redox happens. Let's see the next one. Continuing to work left to right. Halogens are generally -1 unless they are with oxygen, so -1 + 1. That one's easy. Oxygen's -2. Likely +1 acting here. So chlorine must be +1. Oxygen's -2. Sodium's +1. 3 times -2 is -6. Is it -5? So iodine must be +5. So we go through and we're going to do some checking here. So sodium is +1 and +1. It's not that one. Iodine goes from -1 to +5. So that's an oxidation. Hydrogen does nothing. Oxygen does nothing. Chlorine goes from +1 to -1. It becomes more negative. So it's been reduced. Again, all we're doing is we're assigning oxidation numbers and seeing what changes. And hopefully what we are going to end up seeing is we're going to see one oxidation and one reduction. So once again, oxygen's -2. So sulfur must be +4. -2 +1. 3 times -2 is -6. -2 +1. -2 +1 is -8. -6. So sulfur must be +6. So the goal here is to just find 2 things changing. It's ultimately our goal. Sulfur goes from +4 to +6. It's been oxidized. I just used different colors for each one, not necessarily trying to match the oxidation and reduction. Nitrogen goes from +5, so hopefully it dropped, to +2. And there's your reduction. The final one on this set, +1. Your acids are generally going to see hydrogen as +1. It's the acidic protons have generally had their electrons pulled away from it, giving them a positive oxidation state. 4 times -2 should be +6. 2 times +1 is +2. +8, 0. Balancing 4 times negative 2 is negative 8. Negative 1 plus 1. Bromine in its pure state is 0. Negative 2 plus 4. Negative 2 plus 1. 4 times negative 2 is negative 8. Plus 2. It's going to be plus 6. So there's our oxidation states all written out. Hydrogen doesn't do anything. Sulfur goes from plus 6 to plus 6, so it does nothing. Sodium does nothing. Bromine is oxidized. So we got to find the reduction. So sulfur goes from it's sulfur. Sulfur goes from plus 6 to plus 4. It's being reduced. Part of this sulfate is some of it's going to the sodium. The other part is, of course, going and being reduced into sulfur dioxide. So the first one we had no redox, but again, just go through, assign your oxidation numbers, and you need to find an oxidation and reduction for each one. So for question 2021, we are going to have to balance these redox equations using acidic conditions. So the method by which we do this is called the half-celery method, and the steps that you need to do when in acidic conditions are identical each time. So the first thing we do is we just assign oxidation numbers. So anything that's by itself is really easy because their oxidation number is the same as their charge. Oxygen is always -2, so again, that's pretty easy, again, I guess, unless it is in a peroxide polyatomic. So 7 times -2 is -14. Chromium's net charge, the net oxidation number needs to be plus 12 then. So we get this plus this giving -2. So chromium must be plus 6. Iodine in this molecule will be 3 times -2 is -6. It needs to be plus 5. So we make sure we can identify what is oxidizing and what is reducing. Chromium is going from plus 6 to plus 3. That is a reduction. Iodine is going from -1 to plus 5. And that is your oxidation. So once you've identified your reduction and your oxidation, you break them into their half reactions. Cr2, O7, 2 minus, going to chromium 3 plus, I minus 1, going to IO3 minus 1. Again, we're going to ignore states as we go through this. So now that we have that done, we're going to start going through the same sequence we always use. So the first sequence is to identify the balance or anything that is not hydrogen or oxygen. So chromium has 1 here and 2 here, so I'll put a 2 out in front. Iodine has 1 and 1, so we are good. The next thing we'll do is we will balance the oxygens using water. So I have 7 oxygens here. So plus 7 water because each water has 1 oxygen in it. Three oxygen and 3. Always double check your coefficients. Now that you have balanced with the oxygen, you balance with the hydrogens, or you counter with hydrogen ions. So I have 14 hydrogen ions. So I need to add 14 to this side. I have 6 here. So I'll add 6 hydrogen ions. The next thing we will do is we have to charge balance. So 6 plus is plus 6, minus 1 is plus 5, minus 1 on this side. To get these equal, I'm going to add 6 electrons. I have 14 plus and minus 2 is plus 12. 2 times plus 3 is plus 6. So I add 6 electrons to both sides. Now this is nice because the number of electrons in both sides is equal. So we just get rid of those. They're going to cancel. And we just add up these two half reactions now. So 14H plus Cr2O7 minus 2 plus an iodide plus 3H2O gives me 2 chromium plus 3 plus 7 water plus IO3 minus 1 plus 6H plus. Now we just do some tidying up. I have 6 hydrogen and 14 hydrogen, so I'm going to take 6 away from both sides. I have 3 water and 7, so I'll take 3 away from both sides. Now I rewrite with my changes. And there's our balanced equation. We have 8 hydrogens and 8 hydrogens. We have 7 oxygen, and 3 plus 4 oxygen is 7. 1 iodide, 1 iodide. 2 chromium, 2 chromium. This is definitely balanced. So if you've taken a little bit of a break to do these questions, hopefully you'll be able to go through them with me and check to see how you did. So the same story for all of these, just go through and assign your oxidation numbers. Letter B, or problem B here, it does have a little bit of a twist in it. It does have 2 organic molecules. It has methanol and formic acid. So carbon can have a variety of oxidation states. You can sort of decode it just by the molecule itself. We can quickly go through how it was done. We did go through at the first of the course how to assign oxidation numbers to carbons in organic molecules. So oxygens are always minus 2 unless they're in peroxide again, making manganese plus 7. 4 times negative 2 is negative 8. Plus 7 will give you the negative 1 charge. Oxygen is going to be minus 2. Carbon's going to be plus 1. Sorry, hydrogens are going to be plus 1. And that would mean, to make this neutral, negative 2. Negative 2 plus 1 is negative 1. 0 plus 1 plus 2. So this should be negative 2. So negative 2 for this carbon. It's a little hard to make it out. So it should be negative 2 plus 1 minus 2 plus 1. Just remember you can draw the structure out. Look at the carbon. When carbon is bonded to things that are less electronegative than it, assign those bonds a negative 1. If carbon is bonded to something that is more electronegative than to itself, assign it a plus 1. If it's assigned to other carbons, give it a 0. Add up all those bonds and you should get your oxidation state. Manganese by itself is plus 2. So we have plus 1 plus 2 minus 2 +1 on it. Again, you can draw out formic acid and apply those rules again. So manganese is going from +7 to +2. That is a reduction. Carbon is going from a -2 to a +2. That is an oxidation. So we start just by writing out our half reactions. So manganese, oxygen, so permanganate, going to Mn +2, methanol being oxidized to formic acid. So now we just go to work, again, apply the same sequence, balance anything that's not hydrogen or oxygen. So which carbons are good. That was easy. Add water. I need 4 of them. 4 oxygen will balance this one. I have 1 oxygen. I have 2. Counter with your hydrogens. I have 8. I have 1, 2, 3. 1, 2, 3. No, I miscount it. 3, 4, 5, 6, 2. There, that's better. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 8 and 8. So we're good. You can make a pretty bad mistake if you miscount. Go through and do our charge counts. I have 4 plus here. 0. So I'm going to add 4 electrons to this side to cancel out the positives. I have +2. +8 minus 1 is +7. I will add 5 electrons to this side to cancel it out. We need the electrons to balance for us. So I have a 4 and a 5. So the closest we're going to get is 20. So we're going to multiply each side by 4. Change it to 20, 32, 4, and 16. Multiply this side by 5. 5, 5, 20, and 20. So our electrons are gone. We can go through and add it up. Sometimes it's really helpful if the arrows are lined up when you're doing this step. 32 hydrogen ions, plus 4 permanganate, plus 5 water, plus 5 methanol. Gives me 4 manganese, plus 16 water, plus 5 formic acid, plus 20 hydrogen. And we're not going to add that. We're obviously not going to add the electrons in. Let's go through and cancel things out that we see. We have 20 and 32 here. So we'll take 20 away from both sides. (16 water and 5. Take 5 away from both sides. Rewrite the equation. And there's our balanced redox equation. When you're done, you can go through and make sure they're charge balanced and mass balanced. But generally, if you follow the steps and you are paying attention, you should be okay. So the next one we're going to look at is a little bit more straightforward. As always, we're going to assign our oxidation numbers. Iodine in its pure state is 0, -2, and +1. -2, 3 times -2 is -6. So this must be +5. And -1. Chlorine is going from +1 to -1. That is a reduction. Iodine's going from 0 to +5. That is an oxidation. So we got both, so we are good to proceed. Let's write out our equations, our half reactions. I2 goes to IO3 -1, and OCl minus going to chlorine minus. So we have our two half reactions, the ones that are connected by the arrows. Now what we'll do is we'll balance anything that's not hydrogen or oxygen. So we put a 2 in front of the I here. So we have 2 iodine on both sides. The chlorines are balanced, so we're done with that step. Now add water to counter this. So we have 2 times 3, we have 6 oxygen on the right side. So I'm going to add 6 water to add the 6 oxygen to the other side. Plus 1 H2O on the other side. Count. We have 1 and 1. Now we'll add hydrogens to counter. So we have 12 hydrogen on this side. So we will add 12 hydrogen to the other side. We have 2 hydrogen. So we'll add 2 hydrogen. Now we move to charge balance. Start at the bottom right for some reason. -1, +1. Add 2 electrons. On the top, I have 12 plus 12 minus 2 plus 10 electrons. To get to the 0 on this side. So I jumped a step there, but I was at plus 12 minus 2 be plus 10, and this will get us down to 0. We have oxidation and reduction, which is what we predicted up above. The final thing that we should work on is just making sure the number of electrons cancel. I have 10 and 2, so I can make the 2 into 10 by multiplying every coefficient by 5. So we'll do that. Once we're balanced, the electrons should cancel out. Let's add it all up. 6 H2O. Let's just see what cancels out now. Take 5 water from both sides. I guess I just write 1 H2O then. Didn't need to write that out. I have 10 and 12. Change that to a 2. So H2O plus I2 plus 5 OCl. This gives me 2IO3 negative plus 2H plus 5. 2 and 2, 5, 6, 6, 2, 2, 5, 5. That should be balanced. So we'll tackle our last one here, which, again, same method, assign oxidation numbers. -2 for your oxygen. Always -2 for your oxygen. 3 times -2 is -6. So these would be +3 because 3 plus 3 times 2 is +6. 3 times -2 is -6, so they cancel each other. -2 and +5. You start to get very familiar with certain things. 4 times -2 is -8. These are +1s. +3. This needs to be +5 to counteract that. So +3 +5 minus 8 equals 0. -2 times 3 is -6. 2 times +3 is +6. Just using the bottom here just to double check because there's a lot of different things going on here. Let's see if we can find out what the oxidation and reduction were. Nitrogen went from +5 to +3. That is a reduction. AS went from +3 to +5. That is an oxidation. So we've identified what's being oxidized and what's being reduced. So we start by writing out the half reactions. So AS2O3 goes to H3 ASO4. NO3 minus 1 goes to N2O3. Again, we're just ignoring states right now. Now it's the same exact method that we've been working on. Balance anything that's not hydrogen or oxygen. So 2, so AS2, AS, now I have 2 of them. 1 nitrogen, I need to get double. And the order that you do these steps, of course, does matter. So I have 3 oxygen here. I have 8 over here, 4 times 2. So I need to add 5 water. 5 oxygen plus 3 oxygen is 8. 2 times 4 is 8. 2 times 3 is 6 oxygen. 3. And we're going to add water to the other side now. The next step that we will do is we'll add balancing hydrogens. So I have 10 hydrogens on this side, and I have 6 on this side, 2 times 3. So we'll add 4. Down here I have 6 hydrogens and none. So now we charge balance. 0 and 0 is 0. That one's easy. Plus 6 minus 2 is plus 4. So I'll add 4 electrons to equal them out. Up here I have plus 4 and 0. So plus 4. And here I have 0. So I'll add 4 electrons. And that's always nice when the number of electrons is the same on both of them, because it saves us that step. So we can just add these up and then do our canceling. So 5H2O plus As2O3. Again, the electrons aren't going to be written out. And as you get more comfortable with this, you'll obviously start canceling before you add them. So when we go to do this now, it's the same thing we've been working on. Just make sure we cancel things out. I have 6 hydrogens and 4. So take 4 away from both sides. Gives me 2. Water, I have 3 and 5. So take 3 away from both sides. I don't have any other common things on both sides. So 2H2O plus As2O3 plus 2H plus 2 nitrate. There we go. We should have a balanced equation here. Just double check that my charges are in. And we are good. So there we go. We've checked through all of them. And you should be able to, if you can do those 4 questions, you should be able to do pretty much any balancing redox and acidic solution.